Hi everyone. Today we'll take a look at proof by mathematical induction. So, before I get started, proof by mathematical induction is a pretty straightforward process. Essentially we're following three main steps, okay? So, what usually happens in a question, right? The question usually tells you they give you some mathematical expression and they're like prove that it's true by mathematical induction. So you don't really have to think too much. The question will usually tell you that you have to solve this by mathematical induction, right? So mathematical induction consists of three important steps, right? So usually they give you a sequence or a series or some or the other. You'll see a lot of summation questions, or they'll say show that this sequence is a multiple of some integer or something like that, some sort of the other, right? We'll take a look at pretty simple questions since we haven't done a lot of concepts. We won't go into trigonometry or um, a little bit more advanced math. We'll keep it more of simple algebra, just to the point where you understand the concept. And if you are solving a more of a complex problem, you can still apply the core concepts and prove the question, right? So now, first step consists of basically proving that the expression is true for n minus one, right? So if I write, we're saying that proving expression is true for n minus 1. Sorry, not n minus 1, n is equal to 1. I apologize for that. Right? So what we do is we just substitute wherever we have n, we just put in 1, and then we basically make sure that LHS is equal to RHS, right? So LHS is equal to RHS. Okay? Next. Then we make an assumption. And we make an assumption that this statement, that whatever question the question has given us, right? That assumption that the statement or the expression is true for k terms, right? So if it's true for k terms, we can say for n is equal to k, right? We make an assumption that it's true for that. Okay, and the third and final step, this is the most important. This carries the most weightage. That's why I'm going to put a star next to it. It'll probably be a 7-mark question or a 6-mark question where this will be 1 mark, and the rest of the marks will be, on the third step, right? Where we prove that the statement is true for n is equal to k plus 1. Okay, so now what in this third step, right? What we do is we use the expression derived in step 2, and this is vital. It's vital that we do that. Okay, it is important that we use the information that we have in step 2 and then we work towards step 3. Otherwise it's not really counted as an inductive step, right? So step 3 is counted, it's like an inductive step, right? It's called the inductive step because we're using our previous information and moving forward with it. Okay, so this is the 3 steps. Okay, so let's get started with a few example questions. All right, so our first example question is, for all n greater than or equal to 1, prove that 1 squared plus 2 squared plus 3 squared all the way up to n squared is equal to n into n plus 1 into 2n plus 1 all upon 6. All right, so let's work step by step, right? There's nothing to be confused here. So let's put step 1 here. And this is how you should be working in your exam as well, right? Keep it very crisp and clear. You don't need to, jumble everything up. You can just work step by step. So our step says, prove that statement. So we're saying that prove n equal to 1 is true, right? That's our first step, right? So first step says prove n is equal to 2. So if we take, so this sequence is basically n square, n square, n square, n square, right? We're doing 1 square plus 2 square plus 3 square all the way up to n square. So if we take n is equal to 1, what are we going to have? We're going to have 1 square is equal to this part, right? So we're going to have 1, 1 plus 1, and then 2 plus 1, right? Because 2 times 1 is 1, all upon 6, right? So this is our LHS, this is our RHS, right? So we have 1 is equal to 1 times 2 times 3 upon 6. And this is the numerator 6, denominator 6. 6 by 6 is 1. So 1 is equal to 1. LHS is equal to RHS. and hence proved, right? So we can say hence proved. So it's true. So the statement is true for n is equal to 1. Now let me just make a small note here, right? I'll make a small note. For mathematical inductions, right? I'm going to write proof by mathematical induction, right? It's not always necessary that the statement will be n is greater than equal to 1. It can even be it will be greater than n is equal to 2, or greater than n is greater than equal to 2, or greater than equal to 3 or 4 or 5, right? It can even go up to 5. We don't know. So oftentimes you might put n is equal to 1 and it might not be true. So you might have to put in 2, 3, 4 to check. Right? Sometimes the question will even say for all n greater than equal to 5, right? Sometimes it won't. So you be sure to know that. So I'll just reiterate it right here. It's not always necessary that n starts with 1, right? Okay? Just be aware of that. So, some is, for example, you do it and it's not true for n is equal to 1. Don't just, cancel it all out, or don't get so confused about what I should be doing next. All right. So, let's move to step 2 now. So step two, what was step two? Step two said that let's assume that the statement is true for n is equal to k. Right? What it means basically, it's true for n is equal to k terms, right? It's true for k terms, right? K is some definite integer that we have assumed to be, right? Obviously, we can't quantify it. We can't say k is 10 or 11. We have to, obviously k can be 100, it can be 10, it can be 100, it can even be a million. But we're assuming that k is some constant integer that will satisfy the condition. So assume that the statement is true for n is equal to k, right? So all we're doing is just taking our original thing, right? This, and we're just replacing n is equal to k. Okay? So wherever we see n, we replace k with it, and that's it, right? All right, just let me just edit this part. It's actually step 2. So we have, hold a second. So step 2. So we have 1 squared plus 2 squared plus 3 squared all the way up to k squared is equal to k into k plus 1 into 2k plus 1 all upon 6. All right, now let's move to step 3, right? I'm going to change the color for step 3. So now step 3 says that prove that the expression is true for n is equal to k plus 1. Okay, so now if it's true for k is equal to 1, what does it actually mean? It's like we're basically saying that 1 squared plus 2 squared plus 3 squared all the way up to k squared, and then we have k plus 1 whole squared, right, is equal to wherever we have basically k, we're replacing it with k plus 1 because now we have k plus 1 terms, right? Now we're trying to prove it's true for k plus 1. Basically what we did was, okay, so we have the statement, it's true for the first term. So now let's assume that it's true for the next k terms. And if we're assuming that it's true for the next k terms, it must also be true for one term after the kth term, which is k plus 1. So that's what we're going to do here. So we're going to replace k with k plus 1. So we're going to have k plus 1 into k plus 1, which is 2. And then we're going to have 2 times k plus 1, which is 2k plus 2. Or we're going to have 2k plus 3, all upon 6. Okay, this is what we have. Now we have our left-hand side and we have our right-hand side. Now our only goal is to prove that LHS is equal to RHS. Now, note that you cannot put in some integer for k and be like, okay, we satisfied the condition LHS is equal to RHS. You cannot do that. You have to work algebraically, and you have to use the information from step 2 to come and maneuver around and get LHS equal to RHS. So this is the key step, right? This is the most important part of the entire mathematical induction. So this is why I've changed the colors. Now let's look at this part, right? We have 1 squared plus 2 squared plus 3 squared plus all up to k squared. So sum of first k squared terms is this, right? And we have 1 squared plus 2 squared plus 3 squared plus k squared, right? So why don't we do this? I'm going to put purple here, right? So we already have the sum of this, and it's k into k plus 1 into 2k plus 1 all upon 6, right? And then we have this, right? K plus 1 whole squared is equal to RHS, right? I'm not even going to write it. I'm not going to waste my time writing it again and again. So we have this. Now, we've simplified this entire thing, which was like, dot, dot, dot. There's like no quantifiable way to, simplify, but we just did it with the help of step 2. This is important. We have to use step 2 to come prove step 3. If we do not, it's not really mathematical induction. Okay. So now that we have simplified this, right? 1 squared, sum of 1 squared all the way up to k squared is basically this. So all we did was just replace this part, right? I'm going to use a curly brace because it looks better. So I'm just going to do like this, right? I'm going to do it like this. And we have k into k plus 1, 2k plus 1, all the way. This is the sum of first k terms plus the k plus 1 term, and it's equal to all this crap. So let's simplify this. What are we going to get? We're going to get k into k plus 1 into 2k plus. I'm going to make a common denominator of 6. So 6 into k plus 1 whole squared all upon 6. Okay, so now here's the key. How do we how do we simplify this so that it equals this, right? Now we can't open everything up. We can't do 2k squared plus k plus 2k plus 1 and then multiply by k, simplify everything, open everything up and then add it, subtract it, and then factor it out. No, that would be super lengthy, right? And you can probably make a mistake in that as well. So notice we need a denominator. We need a 6 in the denominator, which we already have. So that's good, right? Now what do we need? We need a k plus 1, k plus 2, and 2k plus 3. So we if you see, we already have a k plus 1 here, and we have k plus 1 2 times it, right? Because it's squared. So why don't we factor out a k plus 1? So if we factor a k plus 1, what do we have? Right, we have k plus 1, sorry, and then we're left with k into 2k plus 1 plus 6 into k plus 1 upon 6. I'm going to put the 6 here, right? Now I'm going to try simplifying this. Now I can open this up and still factor things out, right? Because we're trying to get k plus 2 times 2k plus 3 from this right here, right? I'm going to make this in peach again. So this is, and actually, you know what? I'll just put a highlighting color instead. So this should equal to this, right? Logically, that's what should happen. That's exactly what should be happening. So let's open this up. What do we get? 2k squared, right? 2k squared plus k plus 6k, and then we have plus 6, right? So what do we have? We have 3k plus 4k, which is 7k. And here we have 7k. 3 times 2, 6. And then 2 into 2k, which is 2k squared. So exactly the same terms that we're getting. So let's simplify this a bit more. What are we left with? 2k squared plus 7k plus 6. Okay? So k plus 1 into 6. What do we get here? We get 2k plus, what do we have here? So I'm just going to exactly write what we have, right? So I'm just going to write in the same order because we know it's the same thing, right? I opened this up mentally and I saw that it's coming out to be the same thing as this. So all I have to do is I just have to rewrite it the same way. So I'm going to write k plus 2 into 2k plus 3, right? K plus 2 into 2k plus 3. I'm going to extend the denominator bar right here. And that's exactly what we have, right? I mean, you can do it properly, but you have to act smart. You have to work smart in certain ways. You want to save time as well as energy. So now we have LHS is equal to RHS. So we have proved, hence proved. All right, next question. Show that 9 raised to the power n minus 1 is divisible by 8, right? So this is, again, a fairly common type of a question that you will come across, okay? So again, let's get started. Step 1. So step 1, what does it say? Let's go back to the previous example. What did we do? Exactly so we're going to be doing the same thing again. Prove n is equal to true. N is equal to 1 is true. Okay. So let's substitute n is equal to 1, right? So n is equal to 1 is true. So what do we have? N raised to the power 1 minus 1 is equal to 8. Well, 8 is divisible by 8, right? I mean, we don't really need to say anything beyond that, right? Because 8 divided by 8 gives you 1. So hence true for n is equal to 1. Okay, now let's go to step 2. Right, I can squeeze step 2 right here, which is fairly small. Assume that n equal to k is true. Right, we're going to assume that basically n is equal to k is true, but for any kth term, right? If we do this, if we use a sequence, it will be divisible by 8. So what are we doing? We're replacing n by k. Simple, nothing too fancy. So n raised to the power k minus 1, right? It's exactly what we did here in step 2 in the previous question, right? We replaced the statement for n is equal to k. Now, however, I'm going to do one more thing here. I'm going to write something like this, 8p, okay? So why I'm writing this is, right, I'm making sure that it's actually some multiple of 8, right? This entire sequence is some multiple of 8. Why I'm doing this is because if something is a multiple of 8, it's also divisible by 8. So why the reason for me writing 8p is that it's this entire expression is a multiple of 8, so it's divisible by 8, and hence I'm able to write it in a quantifiable manner, right? I can't, how am I going to how there's no other, easy and appropriate appropriate way to express that some expression is divisible by 8, right? Unless until I show that it's a multiple of 8. So this is the reason why I'm doing 8p, right? It's some multiple of. You can use any variable. You can use m, n, o, q, p. Doesn't matter. I use p because I have a habit of using it. All right. So now let's go to step 3. Step 3. So step 3 is what? Prove that n equal to k plus 1 is true, right? N equal to k plus 1 is true. So I'm going to change the color here again like I did last time. I'm going to make it orange. So what are we going to have? We're going to replace k with k plus 1. So we're going to have k plus 1 minus 1 is equal to 8. I'm not going to write 8p because 8p, I've already assigned the p variable for nk minus 1, right? So I can't do that. So what I can do is I can maybe put capital K for this, right? Or if if it's too confusing, I can put p for it. No, not p. I'll put q, right? That'll be better. So I'll put capital Q. Okay. So now I've just changed it up, right? That's all I've done. So now what I'm going to do, I'm going to break this up, right? What do we have to do in step 3? We have to use the information from step 2 into step 3. As you do different questions, you'll be able to manipulate variables around here and there, and then prove step 3. So let's do that. Let's break open this. If we have 9 raised to the power k plus 1, what does it say? It's basically 9 times 9k minus 1 is equal to 8q, right? That's what we have. So now, what is 9k? 9k, right? If I write it here, 9k is actually 8p plus 1. Yes or no? Right? 9, I've just added 1 to both sides, and I've got 8p plus 1. 9k is equal to 8. 9 raised to the power k is equal to 8p plus 1. So let's go and substitute that right here. Okay, so what am I going to have? I'm going to have 8p plus 1 minus 1 is equal to 8q. All right, let's open this up. 72p plus 9 minus 1 is equal to 8q. All right, now let's simplify this a bit more. 72p plus 8 is equal to 8q. Right, now I'm going to factor out an 8, right? I see a multiple of 8, so I'm going to factor out an 8. 9p plus 1 is equal to 8q. And I can stop right here because what do I see? I have this entire expression and I have an 8 outside, right? Outside the parentheses. So what does that actually mean? It means that this entire expression, no matter what it's inside, it's multiplied by 8. So what happens is that it becomes a multiple of 8, regardless of whatever 9p plus 1 comes out to be, right? That's irrelevant. But because I'm multiplying it by 8, right? So what can I say? That it's a multiple of 8, right? 8p 8 into 9p plus 1 is equal to 8q, right? I mean, I can simplify this more and I can say 9p plus 1 is equal to q, but that really doesn't have the same effect. So I can leave it right here, right? Again, let me explain this one more time if you didn't get it. What I did was I factored out an 8 from the left hand side, right? That gave me 9p plus 1. Now we don't care what 9p plus 1 is. It could be 11, it could be 24, it could even be no pi for that matter, although it won't satisfy the condition. But it could be any integer. Let's keep it at integers, right? Because the condition says integers. So 8 into 9p plus 1, right? This is some integer value and is being multiplied by 8, right? So if you get some integer value and you multiply it by 8, so technically it's actually divisible by 8 as well, because you can get, if you divide this by 8, what are you left with? 9p plus 1, right? You're left with 9p plus 1 again. So you're left with the original thing in here because you're dividing by 8. So it is divisible by 8 because it's a multiple of 8. So I mean, I'll just make a small note here. Green. Oftentimes people miss this point. This is the key to solving questions of mathematical induction, especially when they have, show that it's divisible by something. So this shows that it's a multiple of 8, so it's divisible by 8. Okay, that's what it is. And so we can just basically say, because it's multiple of 8, we have that, hence it's proved. Hence we have proved it. Right, that's it. All right, next question. We have 1 into 2 plus 2 into 3 plus 3 into 4 all the way up to n plus 1. And then we have, the expression for the sum up to n terms. So we have to prove that LHS is equal to RHS, right? So let's get started again. Step 1. So let me change the color. Let's make it lime color. So step 1. Prove, right? Again, we're following the same, conventional steps, right? We're not changing anything up, following the same steps again and again. Right? It's a very, redundant process. Prove n is equal to 1 is true, right? So now basically it follows n into n plus 1. So, right? So we're taking the first term. So we take 1 into 1 plus 1, which is 1 into 2, right? The first sequence right here. So we have basically 2 is equal to all this right here. So we replace n with 1. What are we left with? 1 into 2 into 3 all upon 3. So 2 is equal to 2. LHS is equal to RHS. So true. It's true, right? Let's move to step 2. Again, step 1 and step 2 should literally take 30 seconds to solve. It's the step 3 that is the main important. Honestly, it doesn't even matter if you can do step 1 and step 2 if you can't really do step 3, right? This is not even that important. It's like the icing of the cake. The meat of the meat of the question, I would say, is being able to solve step 3, right? That's where you're actually being tested. So let's do step 3. So we assume statement is true for n is equal to k, right? So what do we have? We just replace this with k, right? So we have 1 into 2 plus 2 into 3 plus 3 into 4 all the way up to k into k plus 1, right? And then we have, check right here, k into k plus 1 into k plus 2 all upon 3, right? So let's simplify this a bit. Now let's move to step 3, right? We have step, okay, right, rewrite this. Step 3. Prove n is equal to k plus 1 is true, right? So, again, we're going to write 1 into 2, 2 into 3, 3 into 4, all the way to k plus 1, and then we're going to write one more term. right? K plus 1 into K plus 2, right? Basically, we're replacing K with K plus 1. So K plus 1, which gives us K plus 2. Let's write it down. Right, I'll change the color. So I'll take yellow. So we have 1 into 2 plus 3 into 4. Sorry, 2 into 3. My bad. So we have 2 into 3 plus 3 times 4, all the way up to K into K plus 1. Always write K, what K was, and then write K plus for K plus 1. Okay? Because if you notice, right, for the past two questions, what were we doing? We're substituting the step two, this part of step two, the origins of step two into step three, and then solving the question. So always be sure to write the till k and then k plus one. Don't directly skip to k plus one and ignore this, because then oftentimes it gets difficult to gauge what part we're removing and substituting. Right. This is why I'm always writing k into k plus one. This is the kth. This is till the kth term, right? Even let's look at the previous question, right? So what did I do? I basically, and okay, in this question I couldn't really do much. But I made it in the form of kth term, so I could make the necessary substitution, right? But in let's look at this one, right? I took the kth term and then I did k plus one. So similar, that's exactly what I'm going to be doing here as well, right? So now I can write. Now I'll write k plus one, and then we have k plus two, k plus three, all upon 3. Now we have this part right here, right? Which is basically k into k plus 1 into k plus 2 all upon 3, right? I'm going to do the substitution again. So we're going to have k into k plus 1 into k plus 2 all upon 3 into k plus 1. Right? I'm not going to write the right hand side again. Right? So now let's simplify this. So what can we do? Well, what I can see is I'm gonna first make the common denominator 3. So to do that, I'm gonna multiply and divide by 3 right here. So I'm gonna have 3 into k plus 1 all upon 3, right? Now, again, notice I'm gonna try manipulate. I'm gonna try shifting so it matches the necessary condition, right? Well, there's already 3 in the denominator, 3 here, so we're good with that. Now, I can see k plus 1 in both terms right here. So I'm gonna factor out the k plus 1. I'm going to factor out the k plus 1, and I'm going to factor out a 3, right? So I'm going to get k into k plus 2, right? Hold up. I'm going to make it a square bracket so there's less confusion. Plus 3, right? Now let's simplify this a bit more. What do we get? We're left with k squared plus 2k plus 3, right? Or hold up. K squared plus 2k plus 3. All right. So what I've done is I made a small error here. I put k plus 1, but I forgot to put k plus 2, right? So I'm going to have a k plus 2 here as well. And then another k plus 2 here. So what I'm actually going to have is, right here, I'm going to have k plus 2. What I'm going to have here is 3k plus 6, right? Now, this simplifies down to k plus 1. And then we have k squared plus 5k plus 6, and then we have k plus 1, k plus 2, and then we have k plus 3, right? Which is what k squared plus 5, k plus 6, all upon 6. So we have RHS is equal to LHS, and hence we have proved. Again, we're following the same steps, right? We're not doing anything crazy. It's just depending on what they're asking, we have to make necessary shifts to the condition so that it favors us, so we can simplify it down. Again, I didn't simplify the entire thing, open it up, add them all up, and then factors. No, again, that would have been a very tedious. It's not a very smart way, right? We want to keep it as easy on the eye as possible, right? We're gonna have so many terms. We're like, what are we adding? What are we subtracting? Um, Chances of making mistake, goes exponentially high, right? And time, right? We don't have all day to solve the paper. each paper we have 2 hours to solve it, and we have loads of different questions. And this is one of the easiest questions, right? Algebra, like this entire chapter, sequences and series, proof, whether it's binomial, permutation, combination. This is one of the easiest portions you will get in IB mathematics. So difficulty will increase, right? That is the reality. So you have to decide, right? I can't be spending 15 minutes on a question that should be taking 5 minutes to solve, right? Again, once you practice this, once you do loads of different questions, again, right? I can't do all the types of questions, but what I can do is I can tell you the process that you have to follow, right? I'll do a few more example questions, but just know the process, be aware of the process, and be aware of what you're trying to do. Always keep in mind the end result, right? This is the benefit of doing proofs. You know the end result. I knew the end result was going to be this part right here, right? This was the end result, and I just had to ensure that I somehow, by somewhere or the other, I get on the left hand side, k plus 1, k plus 2 into k plus 3 all upon 6. The moment I get it, I can stop right there, and because I know I've proved it, right? That is all I'm looking to do. Always keep in mind what your end result is, right? If you just do your math, if you do your algebra blindly, right, you'll probably get to a place where you're going, meeting the condition, probably doing the mathematics correctly, but you're not meeting the condition. And proof is not about always doing the math correctly, right? I mean, what I mean by doing math correctly is like expanding this, then then adding them all up, and then factoring out the common multiples, right? I mean, think about it. If I opened this up, I would have had something, this thing open up. So I would have had k cubed, right? K raised to the power 3. Imagine how tedious is that's going to be just to factorize it, right? I mean, that would take ages to do, right? So you have to be aware of what's happening, right? You can't just blindly do the math over and over, right? You have to keep an eye out, right? I'm meeting this condition. All right, I have a 3 at the bottom. All right, now I have I have this, I have that. All right, one more change I'd like to make right here. There's not actually 6, it's actually 3. I was in the I was thinking about the previous question where we had 6 on the bottom. So right, I had a 3, so that satisfies the condition. Let's see if I can get a k plus 1 out. So then now this part goes it's so much more simpler to work with, right? K plus 2 into k plus 3, and I meet the condition, right? What else do I need? That's it. All right, next question. We have 1 plus 3 squared all the way up to 3 raised to the power n minus 1 is equal to 3 raised to the power n minus 1 upon 2. So, you know, I really urge that you try and solve this question on your own. And I can give you a hint. This is very close to geometric sequences and series, right? This is exactly a geometric series where we have first term is 1, common ratio is 3, right? And this is the nth term of a geometric sequence. And if you actually use the geometric sequence formula, it actually boils down to this when you simplify it a bit more. So try it on your own. It's kind of familiar. It's not really exactly new to you, right? So, assuming you have given a go at it, let's get started. So, again, very conventional. Step 1, right? I'm not even going to waste time discussing it at this point. Step 1, prove n is equal to 1. Prove n is equal to 1 is true, right? So, we have 1 plus 3 squared. So, let's take 3 raised to the power n, 1 minus 1, which is 0, which is 1 basically. So, 1 is equal to 3 raised to the power 1, which is 3 minus 1. So, 3 raised to the power 1, 1, 2. So 1 is 1. So LHS is equal to RHS. There we go. Step 1 done. Let's squeeze step 2 in here as well. So assume n is equal to k is true. Right? Okay, let me just rewrite this. It's not good. So is true. Okay. So what do we have here? 1 plus 3 squared. Sorry, 1 plus 3 plus 3 squared. So we have 1 plus 3 squared all the way up to 3. Instead of n, we're going to have k minus 1 is equal to 3 raised to the power k minus 1 by 2. Right? That's what n was. I just replaced it with k. Now, main part. Step 3. Prove n equal to k plus 1 is true. Okay? That is the key part right here. Okay? So, again, let's rewrite this. So we have 1 plus 3 plus 3 squared. And remember, I'm going to write the kth term as well. I'm not going to skip it. So I'm going to write k minus 1 and then 3k plus 1, right? Basically, I'm going to have k plus 1 minus 1 is equal to 3k plus 1 minus 1 upon 2, right? Now, this part is the same as sum to the kth term, which is what we got in step 2, right? Same thing. So let's replace it. That's what we did in the previous questions. That's what we're going to do now. And we're going to continue doing that if we have a question similar to this where we were asked for the sum, right? Where we have a sum in place. So 3k minus 1, 2 plus 3 to the power k is equal to the right hand side, right? So let's simplify this. How am I gonna do it? I'm gonna multiply and divide by 2. So I'm gonna get 3 raised to the power k minus 1 plus 3, sorry, 2 into 3k. So let me rewrite this in a cleaner way. So 2 into 3 to the power k all upon 2. So let's start, fixing things around. So what do we have? We have 3 here. Sorry, we have a 2. We have a 2 in the denominator. We have a minus 1. We have a minus 1. So now technically all we have to do is we just have to make sure that this and this is equal to this, right? We have a minus 1. We have a 2, right? The rest, we just have to fix this up. So now this is actually for I'm gonna write it and I'm gonna solve it and I'm gonna explain exactly what it is. So what do we have? We have 3 times 3k minus 1 is equal to 2. If you get this part, you don't need to listen to my explanation. And then we have 3k plus 1 minus 1 upon 2. And we have proved it. So hence proved. Right? Now let me explain what I just did right here. Okay, so some of you may have got exactly what I did, some of you may have not. That's okay. I'll just explain what I did. Okay. So what I did was I had 2 times 3 to the power k, and I had 3 to the power k, right? Now, at first you're like, how did you get 3 to the power k, right? So think about it. I have basically 1 here, right? 1 times 3 to the power k plus 2 times 3 to the power k. Now, what I can do is I can, take t is equal to 3 to the power k. I can simplify it, make it easy on the eye, right? So what am I going to have? I'm going to have t minus 1 plus 2t, right? Right, I'm just going to work on with the numerator right now. So what am I going to have right here? 3t minus 1, right? Minus 1 was already there. So let's substitute t with 3k again. So 3 times 3k minus 1, right? That's exactly what I did right here. So all that was, I just did some basic arithmetic because it's 3 raised to the power k. I treated that as an entire new variable itself, right? And then I did, the addition. And then obviously you have 3 raised to the power 1 and same base, so you can add the exponents. So I did 3k plus 1 minus 1, right? That's how I got the numerator. Okay, very simple question, right? Nothing too crazy. Follow the same steps. And majority of the questions, again, 90% of the questions will be, a straightforward case and proofs. Sometimes they might make it complicated by putting factorials in it. Right? Again, when we discuss factorials, when you understand how factorials are used, especially in permutation combination, because that's where their direct application is, right? Then you can, then you can do algebra with factorials, and if the question comes with factorials, you can still do it because we're following the same process. The key is not to get diverted or to get confused or scared because you have trigonometry or you have factorial or some other random thing in the question, right? We're following the same process every time. We're not changing anything new, right? Same thing's being applied and same thing will always be applied. All right, let's look at one last question. All right, so we have 2 raised to the power n plus 2 plus 3 raised to the power 2n plus 1 is divisible by 7 for all positive integers. So we've already done a divisibility question before. So let's, you can try this question on your own and then play the video. So let's get started. Again, step 1, nothing too crazy. So step 1, prove n equal to 1 is true. What do we have? We have 2 raised to the power 3, right? And 1 plus 2 is 3. So we have 2 raised to the power 3, and then we have 2n plus 1, which is 2 plus 1. So 3 So what do we have? 8 plus 27, which is 35. 35 is divisible by 7. So I'm just going to write is divisible by 7. So basically, it's hence proved, I guess. You don't even need to do, you can just say hence proved. So I'm not doing LHS equal to RHS. I don't really need to because for n equal to 1, we have a quantified value. If it was k or k plus 1, then I would do, 7p or 7q, something like that, right? Again, step 2, very small part, nothing too crazy. So assume n equal to k is true. Okay, so again, replacing n with k, so we have k plus 2 plus 3 into 2k plus 1, right, is equal to 7p, right? Some multiple, this entire thing will be some multiple of 7, right? And because it's a multiple, it will be divisible by 7, right? That's the whole principle or the whole concept with which we're working on, right? So let's go to step 3 now. Step 3. Step 3 is prove that k plus 1 is true, right? So we assume that it's true for some k integers. If it's true for k integers, it must be true for the next integer as well after k, just k plus 1, right? So what are we going to have? We're going to have 2 into k plus 1 plus 2 plus 3 into k plus 1 plus 1 is equal to 7q, right? So 2 into, now what I'm going to do here, okay, I'm gonna add this here, right? And then I'll just, do everything that's necessary. 2k plus 2 plus 1, 3 is equal to 7q. Now, I have to use this into this, right? How am I going to do that? This is kind of the tricky part, right? This is one of the trickier questions, right? So I have 2k plus 2 plus 3 into 2k plus 1. So what can I do? Now, there's two ways here. I'm going to show you two different ways. And I'm going to work with one approach. You can work with the other approach and try it on your own. You should get the same answer, right? Now, 2k plus 2 plus this is equal to 7p. So what I'm going to do is I can't put this entire thing, right? I can't change this so it meets this condition, right? I can't simplify the left-hand side to meet this left-hand side and then bring in 7p like I did for the previous example, right? But what I can do is I'm going to do something what I did in the example for the multiple part, right? If you go there, I made some adjustments in step 2. So I'm going to make a similar adjustment right there. So I'm going to do 2k plus 2 is equal to 7p minus 3 raised to the power 2k plus 1. And I'm going to adjust this so it meets 2k plus 2. So how am I going to do that? How am I going to do that? I'm going to write 2 into 2k plus 2, right? Plus 3 into 2k plus 3 is equal to the right-hand side, which is 7q. I don't care about that. Now I can put this into 2k plus 2. So what am I going to have? I'm going to have 2 into 7p minus 3 raised to the power 2k plus 1 plus 3 raised to the power 2k plus 3. Okay? Now, let's simplify this. So we have 14p minus 3. Sorry, I'm going to do it like this. Okay? I'm going to put a 2, and I'm going to have 2k plus 1, and then I'm going to have 3 into 2k plus 3. Okay, so now let's work smartly here. We have 14p, right? This is already divisible by 7. I can factor out a 7 right here, and I'm good to go, right? But let's do one more thing. Let's work this out even better, right? I have a 3 raised to the power 2k plus 1. 3 is about 2k plus 3. So what can I do here? I'm gonna make another smart move here, right? And again, this comes with experience. You might be like, how is he doing this so easily, right? And you may be like, oh, he probably has the answer key to the side, and it's fair to judge that, but I honestly don't. I'm doing this right on the spot with you guys. So I'm just trying to manipulate. Remember the end result. What do I need? I need some multiple. I need 7q, or in this case, I just need to be able to factor out a 7 from the entire expression. And if I can do that, that's it. Question has ended. I can stop right there and I can say it's divisible by 7. So the smart move I'm gonna make is I'm gonna make this into this. How am I gonna do it? I'm gonna do it on the side right here. Right? I'm gonna do it on the side. 3 into 2k plus 3. What is this? I can say that this is 3 raised to the power 3 into, or right, hold up. I'm not gonna do it that way. I'm gonna do it this way. 3 raised to the power 2k plus 1 plus 2, right? 2k plus 1, and then the plus 2 is on the other side. What can I say? This is 3 squared into 3 raised to the power 2k plus 1 into 9 into 3 raised to the power 2k plus 1, right? Nothing too crazy. Again, I've kept it very simple, right? Nothing too, nothing too fancied on. I'm just manipulating numbers here and there to satisfy this condition, right? I can't really go from 2k plus 1 to 2k plus 3, but I can go from 2k plus 3 to 2k plus 1, right? Think about it. How am I going to go from 2k plus 1 to 2k plus 3? I'm going to have to multiply and divide by 9, uh, you know, for this here, and then I can sort of do it. But then I'm going to have fractions, and that's messy, right? Fractions are messy. Avoid them, right? I don't like working with fractions. They get messy. The math gets a little bit more tricky, and if things get tricky and time, and if they get lengthy, there's a chance of making a mistake. So I don't want to do that. I'm gonna avoid it as much as I can. So I'm gonna replace this entire part with this. So what I'm gonna have is 14p minus 2 into 3k plus 1 plus 9 into 3 raised to the power 2k plus 1. Okay? Now, treat this like a variable itself, right? I mean, if you want, again, I'll do it quickly again. 14 plus 7 raised to the power 3 raised to the power k plus 1, right, is equal to, what did I have? 7q. Now I'm going to factor out 7. What am I going to have? 2p plus 3k plus 1 is equal to 7q, and hence proved, right? What did I do here? Again, I treated like I can do it again here as well. So I'll just make a separate here. So t is equal to 3k plus 1. So what did I have? I did minus 2 into t plus 9 into t, and I got 7t. And then I got 7, and this is the t part, right? I'll just highlight it. Oh crap, my bad. So 3 and this right here, right? I just substituted back into the place, and so I mean, if you're algebra strong, you don't really need to do this. You can just quickly come here and then get here, right? This is for those people who didn't catch it, who still are struggling with how I'm making such quick simplifications, right? Again, this was the last question, right? I mean, mathematical induction is quite straightforward. Again, there's nothing too fancy about it. The only thing that can get hard, like I said before, is the fact that you're gonna have a little bit of more of a complex concept, which can make it a little tricky. But in the recent years, they haven't been quite simple. They usually give us some example, like this one right here, obviously a little bit more complex, or multiple ones are quite common as well, right? I mean, this one. Well, we have n minus 1 is divisible by 8, right? These are also, the divisibility ones have become quite common as well. Again, following the same process. And yeah, I mean, again, I can go on and on. I can do like 10 more example questions, and it still won't be enough, right? But if you feel like you want more mathematical induction questions, or you want more examples because you feel like it's still not enough, just let me know in the comment section, and I can make a separate questions where I just do at least 10 to 15 different variety of PMIs, so you get a better grip on it and you feel a little bit more confident going into the exam. All right, so that was all for this video, and next video we'll look at proof by contradiction, which is something new, right? Something added quite recently in 2021. So we'll take a look at that, and again, the process will be similar to PMI as well. I'll just do a few questions. Again, there's not, again, there's no end to it. Same like with contradiction as well. So I'll do a few more in that, and that will end proofs. All right. So again, yeah, this was all for this video, and I'll see you in the next one. Bye bye.